So Aidan and I are looking at cutting edge resources for engineering education and the pedagogical potential for this. Okay. So okay. Engineering is a very popular field, yet it's very, very rigorous. Aidan would love to be here, but he's in his final year for computer systems engineering at the University of Georgia. So I'll do the first 15 minutes and kind of skip through, and then he's going to demonstrate activities. I'm more the educator rather than the engineering piece. So we know it's very popular. There are mechanical, electrical, civil, electronics, computer systems. It's a large program at the University of Georgia. I was previously in the University of Georgia system, so I have that connection at the University of West Georgia campus. There are approximately 7.5 million engineers and science graduates in the world, and there are so many innovative resources and such transformation so rapid with technology, as well as with AI. But AI is another set of books. So we won't go into that for this 15 minutes to 20 minutes. So it has a tremendous impact. It has an impact on the job market. And I know a lot of our graduates are concerned, whoa, is AI going to be out of the job? I think the ones in computer programming are far more concerned than the ones in computer systems engineering, but that answer remains to be seen. So we look at various resources, starting with young children in education and moving on through the university level. A lot of this is project-based design, hands-on active learning. You know, this is nothing new. Canada did a phenomenal job back, oh gosh, 50 years or more ago, as far as looking at problem-based and inquiry-based learning, and then that evolved from the medical field, Canada, that one aspect. But if you look at hundreds of years at different programs and different learning styles with apprentice programs, you know, it's hands-on and it's active learning. So we want to look at content knowledge, but also engineering skills and encourage critical thinking activities. So we want to move beyond the standard methodologies and best practices to provide high levels of student achievement. And we want them to have this achievement in authentic real-world experiences. We know they're challenged by a variety of big factors, diverse factors. So engineering educators need to address these unique situations. And there are varied resources, and we look at the opportunity to investigate cutting-edge resources, to focus on the multidimensional aspects of these resources, depending on the age level and the teaching and the learning. So we know that it's a highly valued field. It's extremely important. These contributions are critical to problem solving and innovation. We know the dynamic potentialities through tangible, through significant impacts are realized by focusing on infrastructure and technology as our global challenges are embraced. There are so many rapid technological changes, the challenging economy, the evolving workplace skills, and all this impacts the field of engineering. A lot more women in engineering now. One of my colleagues, actually at Boise State where I work, we had the first woman engineering dean and went on to be a university president, and the first associate dean who was female. I think Syracuse in New York is the only other institution in the United States that had a female dean and associate dean. This young lady here is one of the most highly gifted students. I did a previous presentation on gifted and talented females, And since we have women in the room, I'm going to share this and very, very high IQs. And so I took her picture from that. And so, but we want to look at the contributions that engineering students from all ages have offered, as well as researchers and professors, some that have not been considered. So we have activities, and there are engineering on their phones. And I'm not going to go through all of the review of the literature. It's in the manuscript that we wrote, but it it takes a lot of extra time, and it's there to be read. But there is a tremendous amount of literature on and on and on, especially applied to any kind of inquiry-based, hands-on, problem-based learning, and project-based learning. And there's a small difference in the three, but it's basically engaging students. In fact, that's why Aiden is not here, because in his final courses to graduate, he has all these group projects. He has to be able to group that he would love to come. But we have his piece that he did on a video. So there's tremendous amount of literature, books, as you well know. So I don't need to go through that. So let's talk about resources and learning strategies. And it's not only for the university students and the professionals. The USA National Science Foundation says there are so many resources for students and educators, and we can get online and obtain those on their website and many, many other websites. And we know that learner acquisition is critical knowledge, and that's the goal. And at any age, it can take many different directions. And the methodology related to engineering focuses on the curriculum and content to strengthen knowledge and skills of the profession. And as our previous presenter explained, the mathematical and language expertise in a specific language address was also essential. Aiden and I did another presentation on English language learners. That's a big deal in the United States. We have a tremendous amount of engineering students whose native language is a language other than English. So some of my colleagues do an outstanding job working specifically with international and with engineering students on English language skills. That's also the presentation. So we know as educators, we need to acknowledge and address the opportunities to cultivate engineering interests so that our students can make valuable contributions to the field. And we want to start this at a young age, and that's where my education piece comes in, rather than the nuts and bolts of engineering and that curriculum itself. There's so much going on and so many ways that we can expose students from an early age. And I'll share some of this with you. But educators will incorporate engineering subject-specific labs and exercises according to their learners' abilities. They promote development of content skills as well. And there are resources for all ages and abilities that are very valuable for encouraging students to enter this field. The hands-on active learning opportunities, the engineering classroom with relevant, critical, and analytical thinking, and the multi-level approaches that encourage collaboration, teamwork, problem solving. And all of those are necessary for such a complex field. So if we look at the methodology and pedagogy, we're looking at authentic language learning that incorporate problem solving and the inquiry problem-based learning with the instructional strategies. And these instructional strategies abound. There are numerous avenues to ensure practical application in students' chosen field, whatever field of engineering that interests them and captures their enthusiasm. So it's a combination of the communication, the collaboration, the teamwork, as well as the content skills. So we want an overall educational curriculum that's based on STEM fields to provide the foundation for students so that they can expand their abilities. And then they can concentrate on the engineering field. We need to emphasize careful planning. We need at a more advanced level to look at the multiple sites that exist within the university level engineering activities to build skills that are transferable to the workplace. And that's another aspect. Business and industry criticizes education in the United States for not preparing students to enter the workforce. And we hear from them that they have to retrain students and they have to start it, that we are not meeting their expectations for graduated students who are prepared to enter the workforce. Part of that has to do with collaboration and teamwork. So this fits in there when we encourage them to work together. Okay, so again, emphasizing the hands-on, the English for specific purposes, and helping those students, the interaction, the clarification, questioning, design, and looking at some of our primary language proficiencies for those students who may not speak English as a native language. The visual aids, the diagrams and models are key to overcoming those language barriers. So if we look at a sample of activities, we'll start with the young ones. These are our University of Georgia engineering students. And they are working on concrete experiences applicable to the field. But let's start with the little ones. They're kind of fun. And you know, why not get them engaged when they're young? And some of them have tremendous aptitude. It's absolutely amazing. And better they work on these tasks, you know, the disassembly, you know, their television or radio or cell phone. And some of them, they start at an early age doing that and demonstrate those aptitudes in ways that we might not be too thrilled about. So there are so many activities where they get their learners. And there are STEM toys. I don't know if you're familiar with it, but it's fascinating for all ages now. And there's quite a market for different STEM toys. So parents, one of my friends, my colleagues that I work with, she and her husband are from India. And it's cute. I got tickled because with us, we might put pictures of, you know, oh, my child took his first steps or took she put up, my son worked his first math problem. This was very important to me. And so that was, you know, an example of what was important to her. And they really bought STEM. I mean, this child from the day he could walk, they were both engineers and he was going to be an engineer. And so it's fascinating, all the STEM toys that they have for this age. I saw this demonstrated during the holidays in December. One of the gifts was this rocket, and the children absolutely loved this. There are different kinds. This was called a stomp rocket, and they were out there stomping on this rocket, and it was shooting up and launching things. And so, you know, the STEM rocket toys, they teach physics, the hands-on building, they had to assemble it, launching the air power, they had to understand how to increase air power would make a rocket go higher. It's quite a thing. I think the rocket ended up stuck in a tree somewhere and someone had to fit it down. So that's a very popular one for the younger ones. So all these different kids. Perfect. Okay, so I'm gonna rush to this because I don't want you to see he's far better than I am. And he's the real thing. So thank you. So example, physics. At secondary of high school, at high school level, but a lot of collaborative activities, tools. We talked with Evan Caspary, who's 15, and he told me about different activities in his engineering course that they did to work with 3D printers to make USB drives. Okay. and then fusion modeling software. Okay, constructing fully solar cars, and let's turn it over to Aidan though. So this is the university. These are our university engineering students. And Aidan is going to talk to you about passengers. So, how they're made, real world use, don't ask me to explain this. And so, Aidan should be there, for Aidan. Where's his video? It's supposed to be right here. That's the version. It's supposed to be embedded.
But this is a PDF file. It cannot be embedded.
Okay, well, they already told me it was embedded and it was right there. I'm gonna say.
So that brings the
A lot of fishing.
link here.
Perfect.
This. This one?
No, it's. It's
Sorry.
a video. There he is. He's 21 years old.
This is a demonstration of how an activity using capacitors would look and kind of how to build the circuits for it. So first we're going to charge the capacitor, and there's the charging circuit. We have a 9-volt battery, a 10K resistor, there's the capacitor, and there is the LED in the circuit. So the capacitor is going to charge up to the battery voltage, which is 9 volts. So I'm going to go ahead and plug the battery into the breadboard. And then when we plug in the capacitor to the circuit, we're going to see the capacitor, or we're going to see the LED initially light up. And as the capacitor gets closer to the battery voltage, we're going to see the LED get dimmer and eventually turn off, because once it reaches the 9 volts, then it won't let any more current through. So just plugging the capacitor in, we can see LED is turned on right now. And the amount of time that the LED is going to be turned on is going to be determined by this formula. Tau equals RC. So the resistance is 10K and the capacitance is 470 microfarads. If we multiply those together, we get 4.7 seconds, but it takes 5 tau for the capacitor to fully discharge or charge. So if we're doing a kind of a time estimate of how long it'll take to charge, it should have taken about 23 seconds to charge. And the discharge time should be about the same. So now plugging it in to the discharging circuit, we can disconnect the battery since the capacitor is going to act as a battery, and plug it into here. It should take about 23 seconds to discharge, and there's the circuit for that. We can see the capacitor is going through the 10K resistor and into the LED. And the formula from earlier, we can really just, using this, calculate different, or we can change the charging time of it by changing the resistance or capacitance value, and that could be helpful in different circuits. And I mean, we could also, the reason we have this resistance here is because without the resistor, we would have a close to 0 as the resistance value, and that could, it might burn out the LED, or it could also damage the capacitor, just putting that much energy in it so fast. And you can also kind of look at what capacitors are used for in a lot of circuits. I mean, capacitors are one of the kind of fundamental building blocks of circuits. The main ones are resistors, capacitors, diodes, inductors. Those are kind of the main components that make everything else up. And capacitors in DC circuits, which is what we're looking at right now, the capacitor usually just blocks DC signals, but that can be pretty useful. We can see in this circuit, it would be like if we have a DC signal and an AC signal, then the DC signal would be blocked by the capacitor, so it wouldn't be able to connect to ground, but the AC signal would be able to get through the capacitor. So pretty much what this would do is just filter out noise in the circuit by only allowing the DC signal through. That's how they're used in a lot of circuits. They have a lot of other uses once you get into AC circuits, and they're used a lot of the times to just filter out low and high frequencies in those circuits. And that's pretty much it. This only really takes some resistors, LEDs, the 9-volt battery and the capacitors. Yeah, thank you.
Diane, would like to miss.
Lo sapevi che le belle vetrate scorrevoli si installano in una giornata e senza permessi? Adesso ottieni il 40% di sconto immediato e detrai.
Thank you, thank you. My husband said what Aiden didn't tell you, but you all know, is be careful of those things, because they will shock the heck out of you. And he said when he was in college, that the teacher, maybe it was high school, would put one on in his desk. And then with the ground there, and so if kids came up and fooled around, it would shock them. Nowadays, the teacher would lose their job. The parents would complain, the teacher, but in those days, So do you have any questions? Can I, anything?
Have you finished?
Yeah,
Thank you very much for your presentation. 3 minutes for question.